Okay, I'm going to talk about the pozzolanicity of supplementary cementitious materials. Keeping on with the theme of concrete, a lot of people kind of say, concrete's really bad. It contributes 5 to 10% of man-made CO2 emissions. And that sounds like a truly dreadful number. And it is. But then you got to think about the fact that we use more of concrete than just about any other material except for water. So if you actually look at the embodied energy data, cement is pretty low. Concrete is even lower because concrete is only about 15% of cement or something. So this is an issue of scale. It's not that the concrete or the cement is bad in itself. However, we can still do better. And what we have been doing, cement scientists or concrete material scientists for the last 50 or so years, or a little bit longer than that, is we've been replacing cement with supplementary cementitious materials. These are typically waste aluminosilicate materials, which increase the concrete durability and sustainability. And a whole bunch of them look like this. The problem is we do not have enough supplementary cementitious materials. As you can imagine, finding a billion tons of materials, no, several billion tons of materials every year is not that easy. So we have shortages both locally and globally. This means that we must identify novel supplementary cementitious materials. Problem with doing that, and I could talk for hours and hours about this, but the standard tests for doing this are actually extremely inaccurate. They do not measure any sort of fundamental behavior. They just, they're from like 30 or 40 years ago, and they're dumb. Let me just put it that way. So we need to develop new, better test methods. So what we've been doing is actually, we try to study the fundamental process of what's happening. That fundamental process is simply that supplementary cementitious materials react with calcium hydroxide. Calcium hydroxide is not good for the concrete. That reaction produces calcium silicate hydrate, which is good for the concrete. So if a supplementary cementitious material is reacting with calcium hydroxide, that's a good indicator that it's good for the concrete. So we have to identify this reaction. So what we do is we have a model system of supplementary cementitious materials, calcium hydroxide, crudely illustrated there. There's a couple of other variables. I do not get into the details of that. And essentially, we measure two things. The first thing is how much calcium hydroxide is consumed. And the second is how much heat is released. These are actually not identical for somewhat slightly complicated reasons. And those are the test methods that you use to do that. That second picture is from a while ago. Unfortunately, I'm not allowed in the lab anymore. So, well, I'm not allowed because my students get scared when I'm there standing behind them. But just kidding. So anyway, moving on to some of the results. So this is from about 50 different materials, including about 10 or 11 different classes of materials. And actually what we see is that this material classification system that we've developed, you actually get about 5 or 6 different classifications of these materials. You have highly pozzolanic, more hydraulic, pozzolanic. These are good materials. We want to use them in concrete. Interestingly enough, almost all the conventional SEMs that we tested fall in that category. Not very surprising. And then we have inert, which is really not doing very much, and less hydraulic. And these, for the most part, are not that effective as supplementary cementitious materials. We tested 3 new materials. One is fly ash coming from the burning of municipal waste. You can imagine that something like this is a material that's going to be very commonly available in the future. The other is a slag coming from the iron making industry. Both of these materials are from China. Unfortunately, they're really new materials, but they turn out to be not very useful. The third is a powder coming from grinding of lightweight aggregates, which is used very commonly in concrete. That one actually turns out to be pretty good. We don't have to worry about the individual classifications. The idea is that if you have something that's over x equals 60 and y equals 200, you probably have a really good material. Right now, we're actually looking at, depending on the classification, what sort of replacement level of cement and concrete can we use. There's actually quite some science into this as well. So we took all of those 50 materials, grouped them into 3 different types of materials depending on their chemical composition, and this is just a bulk chemical composition. So depending on their calcium, alumina or silica content, you actually get very different slopes, and this seems to arise because of different reaction enthalpies. And this is really nice because then we only need to measure one of these 2 tests to actually get the other one. So the idea is we can actually predict fundamentally from the chemical composition the response. So to conclude, we propose a new test. This test seems to work really nicely so far. The relationship seems to depend on the chemical composition, and in the future we look to study more new materials as well. Thank you very much. If you want to talk about cement or concrete, shoot me an email, catch me in my office. Thank you.
Thank you very much.